These are notes from section 7.5 in your textbook titled Exponential Models. First thing we need to do is define what an exponential function is. We've been dealing a decent amount with exponents. An exponential function is an equation with a variable in the exponent. So remember, a variable, that's a symbol, usually a letter, that fills in for a number, and it can change. Usually we use x and y as our variables. So notice the x needs to be in the exponent. So like y equals 5 to the x is an exponential equation because x is in the exponent. Whereas y equals x to the 5th is not an exponential equation. Even though it has an exponent, the variable, the x is not in the exponent. So this is not exponential. This is an example of an exponential equation. And there's lots of ones that we could have. 3 times 1/2 to the x is also an exponential equation. So again, an exponential function is an equation with a variable in the exponent. These two are exponential equations because I've got x, a variable, in the exponent. One like this, even though it has an exponent, is not an exponential equation because the x is not in the exponent. It's down here as the base. This is a polynomial, which we will look a little closer at next chapter. The graph of an exponential function will look something like this. So we've got our coordinate plane. It starts close to the x-axis and it gets bigger and bigger. So as our x value gets bigger, the y value not only gets bigger like a line, but the slope of that curve continues to get bigger and bigger. It could look like that, or it's also possible that it starts up high and then comes down low. And we'll talk a little bit more about how we get that graph and how to tell the difference between these two here shortly. So the graph of an exponential equation is going to be in the shape of one of these two. The first thing we're going to do is graph an exponential equation. We're given y equals 1/2 times 4 to the x. Y equals 1/2 times 4 to the x. To graph this exponential equation, we're going to make an xy chart. And for these, we are just going to plug in 0, 1, and 2 in for our x's and get our y's. So to graph an exponential equation, we make an xy chart. The x values we're always going to plug in are going to be 0, 1, and 2. So if I plug 0 in for my x, my equation would say this: y equals 1/2 times 4 to the 0 power. Order of operations, remember, our parentheses first. Parentheses, I've just got a 4. And then we do exponents. So the next thing I do is 4 to the 0 power. Earlier this chapter, we said anything to the 0 power is 1. So 4 to the 0 would be 1. And then we multiply and divide and then add and subtract. So we always want to do the exponents before we multiply. So I did the exponent first, and now I do 1/2 times 1. If I plug in 0 for my x, I get 1/2 for my y. Now we want to plug in 1 for our x. So I have 1/2 times 4 to the first power. 4 to the first power is 4. 1/2 times 4 gives me 2. And now we're plugging 2 in for our x. Putting 2 in for the x right here. If I put 2 in for x, it's going to say y equals 1/2 times 4 to the second power. 4 to the second power means 4 times 4. That's 16. 1/2 of 16, 1/2 times 16 is 8. So we've got 3 points there. 3 points should be enough to draw a good graph. I've got my x and my y. I need a point at 0, 1/2. So my x value is 0, my y value is 1/2 is going to be right there. And I've got a point at 1, 2. And a point at 2, 8. X is 2, y is 8. These graphs always get close to the x-axis. Technically, they never touch it, although it's okay if it looks like it touches the x-axis. What we can't have is it doesn't cross down underneath the x-axis. So it should not look like this, where it goes, whoops, that's bad there, where it goes under the x-axis. This part of my graph over here on the left should stay close to the x-axis. And my graph should look something like this. Let's try another one. Example 2 says y equals 6 times 1/2 to the x. Y equals 6 times 1/2 to the x. Again, we want to start by making an XY chart. The values we plug in for x are going to be 0, 1, 2. 0, 1, 2 should give us a good enough graph that we can sketch in that curve of the exponential function. Plug in 0 for your x. Y equals 6 times 1/2 to the 0. Anything to the 0 power is 1. So I get 6 times 1. 6 times 1 gives me a y value of 3. Plugging in 0 for x. Holy cow. 6 times 1 is not 3. What am I doing? Plugging in 0 for x gives me a y value of 6. Now we plug in 1 for our x. Y equals 6 times 1/2 to the first power. I'm putting 1 in for my x. 1/2 to the first power is 1/2. 1/2 of 6 is now 3. There's my 3. Put 2 in for x. 6 times 1/2 to the second. 1/2 to the second power, there's a couple different ways you could do it. Second power means multiply it by itself, so we would do 1/2 times 1/2. And then to multiply fractions, we just multiply straight across. 1 times 1 is 1. 2 times 2 is 4. Another way we could do it, we have 1/2 to the second power. We had a property last section that said if I divide and I raise that to an exponent, I can distribute this exponent. So that would be the same as 1 to the second over 2 to the second. 1 to the second, 1 times 1 is 1. On the bottom, I've got 2 to the second, 2 times 2 is 4. So either way, I should get 1/4. 1/2 squared gives me 1/4. 6 times 1/4. 6 times 1 over 4. 6 is the same as 6 over 1. Multiply across. 6 times 1 is 6. 1 times 4 is 4. So I get 6 over 4. My I can divide the top and the bottom by 2. Gives me 3 over 2. We can write it as 3 over 2. 3 over 2 might be a little more difficult to graph because we might not conceptually see where that's at. 3 over 2, remember, is the same thing as 1 and 1/2 or 1.5. That might be a little easier to graph as 1.5. On our coordinate plane, we plot those points, 0, 6. 0, 6 would be right there. 1, 3, x is 1, y is 3, and 2, 1.5, 1.5 would be right there. Again, remember exponential functions, they should not go past the x-axis, they shouldn't come down here at all. So it's going to look something like that guy there. I want you right now to pause the video, and I want you to try these two. So you, on your own, see what you can do with those two problems. Once most of the class has them complete, you can go ahead and play, and we'll talk through them. So the first one, I'm going to do the first one in red here. We make our XY chart. We plug in 0, 1, 2. Plugging in 0 in for x should give me 1 times 8. Plugging 1 in for my x gives me 1/4 times 8, which is 8 over 4, or 2. Plugging 2 in for my x, 1/4 times 1/4 is 1 over 16. 8 times 1 over 16, 8 times 1 is 8. 1 times 16 is 16. I can divide the top and the bottom both by 8 to get 1 over 2. 1/2, 4.5. And now we've got 3 points. We should be able to draw our graph. 0, 8, 1, 2, and 2, 1/2. And again, our graph should get close to the x-axis there, but not cross it. Second one I'm doing in blue. Again, XY chart, 0, 1, 2 in for x. If I put 0 in for x, I get 1 times 3. Putting 1 in for my x gives me 2 times 3. And 2 in for my x, 2 squared is 4 times 3. So we've got 0, 3, 1, 6, and 2, 12, which is a little bit off my graph. So my graph should look something like that guy there. These two graphs look different. This one starts low and goes high. This one starts high and comes down low. Same with these two. This one here started high and went low, whereas example 1 started low and went up high. I want you to think for a minute. Take a look at those 4 equations. So the red one and the blue one, as well as the ones in examples 1 and 2. I want you to think for a minute how we could tell if it's going to be an exponential growth graph. Growth means gets bigger. So this blue is a growth graph. Or if it's an exponential decay graph, which is the red one here. So obviously, if you draw the graph, you can tell. I want to know just by looking at the equation. So 8 times 1/4 to the x gave me decay. 3 times 2 to the x gave me growth. 6 times 1/2 to the x, that looks like decay. 1/2 times 4 to the x is growth. So here we're talking just a minute about how we can tell the difference between exponential growth and exponential decay. What I hear a lot is if the number raised to the x is a fraction, it's decay, which is true in this one and is also true in this one here. Although 2, we could write 2 as 2/1 and it's a fraction, right? And that's still growth. So it does have to do with the value that's right here. Let's take a look. I have y equals a times b to the x. I have something times something else to the x. So the number that matters is the b. Whatever we're raising to the x value, that is what determines if I have growth or decay. If b is greater than 1, then we have exponential growth. Y equals a times b to the x is exponential growth. If that b value is less than 1, then y equals a times b to the x represents exponential decay. So going back and looking at these two, if I were to want to know if the red graph, y equals 8 times 1/4 to the x, is growth or decay, I would look at the b value, 1/4. Since that's smaller than 1, I know it's decay. And once we draw our graph, it is. Here, 2 is bigger than x, or I'm sorry, 2 is bigger than 1, therefore it is exponential growth. So let's call this example 3. For each of these, I want you to answer this question. Do we have exponential growth or do we have exponential decay? And here we have y equals 2/3 times 5 to the x. 2/3 times 5 to the x. So first of all, make sure you're looking at the right number. It's always whatever we raise to the x, in this case 5. 5 is bigger than 1. Because it's bigger than 1, it is exponential growth. Let's do y equals 3/4 to the x. Y equals 3/4 to the x. Again, I'm looking at the number in parentheses, the number that's raised to the x. 3/4. 3/4 is smaller than 1. Therefore, we have exponential decay. Part C, y equals 9 times 5/2 to the x. 5/2, because the top is bigger than the bottom, I know that that's bigger than 1. It's 2 1/2. Therefore, we have exponential growth. If you're having questions about anything, please reach out. Let me know. I'd be happy to answer them.